Let's start with the basics. We will learn how to visualize relationship between two variables and also how to assess the strength of this relationship. So let's start with the visualization. Any dataset where you have two or more numeric variables can be represented as a scatter plot in variable space. What do I mean by that? You can see here already is that we have dataset with two variables. You can think about something simple like height and weight of people. And these are individuals, so these are persons. So, for example, every x inside this matrix is just a number. Okay. Now, the first idea is that every variable is an axis in the Cartesian space. So in this case, I have two variables. So I will have two axes, x1 and x2, or x and y, as you used to. And that gives us the two-dimensional Cartesian space, a plane, right? So this is x1, this is x2. So that's what we call a variable space. Now, every object, every individual is a point in this space. Let's think how we can make this point. Well, if you take one particular person, it has one particular weight and height, right? So, for example, 170 centimeters and 70 kilograms here, right? So you have 170 centimeters here, you have 70 kilograms here, and then you have intersection of these two numbers, right, on the plane. So this is coordinates of the points. So this point has two coordinates, 170 and 70. And that's exactly where your individual is. So individuals are points in the variable space. You can think about data as a data cloud. It's a cloud of points. And therefore, if you look at this cloud of points and find any patterns, any geometrical patterns like different trends, so they are stretched in one direction, for example, clusters, outliers, anything that gives you an information about this relationship. So that's the patterns, the geometrical patterns, they actually visualize this relationship. If you go back to the tabulated data, the people data, we have 32 persons and 12 variables, and the variables are very different, and most of them are numeric by nature. Some of them are numeric because I turned them to numeric, right? So let's take different pairs. For example, let's take height and weight and make a plot, a scatter plot. Or let's take beer and wine consumption and make a scatter plot. Or let's take, for example, income and age and make a scatter plot. So let's make different scatter plots for different pairs of these variables. That's exactly what you see here. So let's take one by one. So this is height and weight. And you can see that I added another important information on top of this plot by using color. So color is blue for males and red for females. So you can clearly see that in this case, you have clusters. You have male cluster here. You have female cluster here. They are not overlapping. So it means that in this particular data set, males are taller and heavier than females. You can also see some patterns, like, for example, this is an outlier here. And these two ladies, they do not follow the common trend. You can see this is the common trend, right? The points kind of line on a straight line. But these two ladies, they deviate from this common trend, right? So you can already see a lot of patterns here. This is beer and wine consumption, right? You can also see that there are some clustering here, but not as strong as the previous plot. And you can also see a kind of trend, right? So you can kind of a linear trend here, which is weaker than this trend. You can think about this trend as well, right? And also you can see that it has other direction, because in this case, the slope of this line is positive, the slope of this line is negative, right? So it means that when one variable goes up, the second variable goes down, and vice versa, right? This is income and age, and we still see the positive trend, right? When income is higher, age is higher, so probably we should swap these two variables. So age is higher and income is higher, because I believe it's age that causes the income, but we will discuss this causality issue also in the block number 3. And then you can see that wine and age, you don't see any clear patterns here. The plot points are just scattered chaotically in this plot. So it means that most probably, at least by visual inspection, we don't see any relationship between wine and age. Right? So you can see that plots help a lot. We see a lot of different patterns. And one of the most important patterns for block number 3, it's this relationship or moreover linear relationship. So you can see that in most of the cases, you can make a line which kind of fits the trend of these points, fits the variation of these points quite well. So let's learn how to evaluate this relationship. So how to evaluate this linearity between these two variables, how strong this linearity is, how weak this linearity is, and so on and so forth. And then later we'll also learn how to define the coordinates of the parameters of these lines. Okay. The first important statistics is covariance. But to understand covariance, let's recall what variance is. We already know the variance, right? So variance, it's a statistic we use to show how variables vary, right? So how big the spread of the values is. How we compute the variance? We compute variance, it's a sum of squared distances between every point and the mean. So for example, if we take this point and if we take the mean, right, we simply measure how far this point is from the mean. So we measure this distance. Then you remember we square it. So in this case, I don't square, but I multiply distance to distance. It's the same as just xi minus mx squared, right? It's the same. We square this distance because we are interested only in the magnitude of this distance. We are not interested, is it below average or above average? And then we take a sum of squared distances and divide to degrees of freedom. That gives us the average squared distance. That's what we call a variance, right? So variance tells you how far values can go from the mean for one particular variable. Covariance, it's a similar statistic, but for two variables. So in this case, you can see that the main difference is following. Instead of square the distance for x, we multiply it to the corresponding distance for y, where x and y are two different variables. Again, let me illustrate it. So now you have x and y. For example, this is height and this is weight of people, right? And you can clearly see this linear trend here. So how we can measure this trend? Well, we simply find average. Let's take a point again. We simply find average for x and then measure how far this point is from the average from x along the x-axis, similar to what we have here. But now we have one more variable. So we can do the same trick for the second variable. So we take the average of y and measure how far this point is from the average of y in this direction, right? And then we multiply these two distances. So strictly speaking, what we measure is an area of a rectangle, which formed by these sides, okay? However, if you have, for example, if you have a point here, then this area that we compute like this will be negative, because in this case, x minus mx will be positive, right? It will be above 0. But y minus my will be negative, So that's the only difference between area and these terms in covariance. So in these terms, we can have also negative values. So we will discuss the meaning of the negative values in a minute. But the idea is following. We compute all these, the areas, and then we take a sum of these areas. And then we divide to degrees of freedom, similarly to the variance, which means we compute a average area, okay? Now let's discuss it a little bit more. First of all, you can see that here you have x minus mx squared. Here you have x minus mx, y minus my. And actually later we will also use a lot of these squared distances. In order to simplify most of the expressions, let's introduce special names, special acronyms for this kind of distances, okay? So these acronyms are called all sum of squares. So it means it's a sum of squared values. The simplest sum of squared values is just to take the value and square it and take a sum, right? So this is how to compute it. And that's what we will denote like SS and then letter which show the variable name. So SSX, capital S, small x, means sum of squared x values. Sum of squared x values. Now, if you compute sum of squared distances, right? So you have x minus mx, and so on and so forth, exactly what we do in variance. We will just double this index. So SSXX, it means it's a sum of squared distances between x and its average. And that's what you use to compute variance, right? And then SSXY, we will compute a sum of these areas. So when you take the distance for x and distance for y, and then take a sum of this product of these two distances. So this is SSXY. This is not strictly speaking sum of squares, right? But it's we use SS anyways, like a sum of squares. So now we can simplify our expressions by just showing this sum of squares for distances between x and average x, and this is just a product of two distances x minus mx and y minus my. So that will simplify a lot of calculations as well. Okay. So now let's discuss the covariance in a little bit more detail. So let me show you an example. So this is my data set. It's just some abstract two variables, x and y. You can think about anything, any two variables, numeric two variables. If I compute average, I will get 8 and 8 in both cases. And this is the distances. You can see that, for example, this is minus 2 because it's 6, minus 8, right? This is minus 1 because it's 7, minus 8, and so on. So these are the distances. So if you want to compute covariance, you need to multiply these distances to each other. And then you can see this is negative, negative, it'd be positive, 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 positive. Again, negative, negative, it's positive. Negative, negative, it's positive. And these two distances will be negative, right? So these 2 points contribute negatively to the total covariance. And these 2 points contribute positively to the total covariance. Of course, the overall covariance will be positive as well because you have too many positive contributors here, right? Let me visualize this. So this is the plot. So I just removed all the drawings. And now you can see that all the points, most of the points share this linear trend and only 2 points do not, right? It's these two. And that's exactly these 2 points which negatively contribute to the covariance. This is the total covariance. It's average product of these two distances. It means that you take a sum of these products and then divide the n minus 1 to degrees of freedom. And this is the positive covariance. So we can see a positive covariance. It means when one variable goes up, the second variable goes up. You can actually spot it also from the data set, right? So you can see this is the biggest value here, and it's also biggest value here, right? The larger x is, the larger y is. The larger x, the larger y, and then the smaller x, the smaller y. Okay. Now let me show you another example. So in this case, you can see that, again, if you look at the data, this is large, this is small, this is large, this is small, this is small, this is large, right? So we have a kind of opposite direction of the variation. So let's measure it. First of all, the average values are the same. And then if you compute the distances, you can see that most of the time you either have like positive and negative distance, or you have, for example, negative and positive distance. So it means that the product will be negative. And if you take a sum of many negative values, you will also have a negative value, right? So this is how the data set looks like. You can see that it also has a linear trend, very clear linear trend, but this trend has an opposite direction. What does it mean? It means when x is large, y is small, and vice versa. When x is small, y is large. So that's a negative covariance. So positive covariance when both values vary together in the same direction. And in this case, the variables vary in opposite direction. When one variable goes up, second variable likely goes down, and vice versa. That's why if you compute the covariance, you can see it has almost the same number, minus 16, but it's negative. So this is negative covariance. Finally, if you look at this example and compute the distances, you can see that sometimes it's positive, positive. Sometimes it's positive, negative, 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 positive. So you have all kind of variation here. And if you look at the data, you can see indeed, although most of the points align in these two quadrants, right, in these two parts, you can see these 2 points are very far away. And you remember that covariance, contribution of the covariance, it's this area. So it's important how far this point is here, right? And this point also will contribute negatively. So you have some points with negative contributions, some points with positive contributions. And if you calculate the total covariance, you can see it's almost zero. In this case, it's small negative covariance, minus 1.2, right? So in this case, we can say that there is no covariance. So it means that there is no relationship between these two variables. It means that if one variable goes up, the second variable likely can go up or can go down or can remain the same. So there is no strict relationship between these two variables. Okay. So this is just schematically the overview of contribution. So every time your point is in this part or in this part, it contributes positively to the total covariance. Every time your point is in this part or in this part, it contributes negatively to the total covariance. So you have most of the points from the red parts, your covariance will be positive, and there will be a positive trend like this. If most of your points are in this negative, in the blue parts, the covariance will be negative, and the trend will be negative as well. But if you have the same number of points approximately in each quadrant, then the covariance will be 0 or close to 0, right? There are two important things that All this makes sense only if you indeed have a linear dependence. If your dependence is not linear, then you need to find another statistic that also will serve as a covariance, which will tell you how strong this relationship is. And also, the covariance is maximum always when all points align on a straight line. But we will discuss this also in the next video. Okay. Now you know a new statistic, which tells you something about how strong linear relationship between two variables is. In order to understand this better, I recommend you to go to Grasta. If you take my course from the e-learning platform, then you will have this app in the platform, incorporated to the platform. If you watch it from YouTube, you go to Grasta and take the covariance app. In the next video, you will see, as usual, a small introduction into the app, and then I highly recommend you to go and play with this app and then come back to this learning sequence.